Hi, welcome to Intermolecular Forces, Solids and Liquids. My name is Dr. English. Today we're going to talk about phase diagrams and enthalpy changes. Specifically, we're going to be looking at phase change overview, review of heating curves, calculating enthalpy changes in phase diagrams, review of some formulas, and finally some enthalpy change practice. Let's start out by reviewing phase changes. Phase changes are defined as the conversion of a substance from one state of matter to another state of matter. Here we have some phase changes. For solid to liquid, if it's an endothermic process, we're going to be looking at melting. If it's an exothermic process and energy is released, we're going to be looking at freezing. The fancier way of saying melting is fusion, and freezing, we use the term solidification. For the phase change of going from a solid to a gas, that's known as sublimation, and we can see this process in this image over here. Going from a gas to a solid is known as deposition. The phase change of liquid to gas is known as vaporization, and the opposite of that, gas to liquid, is known as condensation. Let's do a little review of a heating curve. This heating curve basically represents three phases: solid, liquid, and gas. As we go from the solid to a liquid, we see that if we add energy, we experience melting, and if this is an exothermic, we experience freezing. Going from a liquid to a gas, that's evaporation or vaporization, depending on the situation, and from a gas to a liquid, that is condensation. The big thing that I want to point out here is that during this process of phase change, here and here, that the temperature remains constant. So we want to make a note to ourselves here. Temperature remains constant. That is a key thing to remember for both the situations here and here as you're looking at these phase change curves. Calculating enthalpy changes in phase diagrams. Recall that enthalpy changes associated with any process depends only on the amount of matter that undergoes change and on the nature of the initial state of the reactants and the final state of the products. The sum of the enthalpy changes associated with the individual steps must be the same as the enthalpy change associated with a one-step process. This is reminiscent of Hess's law. Couple of formulas that we're going to use as we calculate enthalpy changes in phase diagrams. The first is Q equals mc delta T, where Q is our amount of energy in joules, m is our mass, C is our specific heat capacity, and delta T is our change in temperature. The key thing that you need to remember here is that when you do delta T, it will always be temperature final minus temperature initial. That is very important to remember. Q equals delta H fusion times either the moles or grams talks about the heat of fusion. Q equals delta H vaporization times either moles or grams talks about finding the heat of vaporization. All three of these formulas will be used in our next example. There are a number of steps that you're going to want to follow as you calculate enthalpy changes. The first is to draw out the phase diagram of the energy changes. The second is to determine the number of steps involved in the calculation. That is key. Finally, identify the formulas needed to find the overall amount of energy absorbed in the system. So let's look at an example. Calculate the enthalpy change associated with converting 45 grams of water at 25 degrees Celsius to steam at 115 degrees Celsius in 1 atmosphere. So the first thing that I'm going to do is draw out my phase diagram. So I'm going to do this, and I can see that this is a heating curve because I'm going from 25 degrees Celsius to 115 degrees Celsius. So I'm going to do solid, liquid, gas up to here, extend this out a little bit. I know that I am working with water because it states that right here. So if I know that this is a solid, a liquid, and a gas, then this point right here is going to be 0 degrees Celsius, and this point right here is going to be 100 degrees Celsius. The next thing that I want to do here, once I have those two things marked out on my phase diagram, is I want to know where am I starting and where am I finishing. So I'm starting at 25 degrees Celsius and I'm going to 115 degrees Celsius. So that means I've gone through the solid to the liquid stage. So maybe I'm, I don't know, right here. We'll say that's 25 degrees Celsius. And 115 degrees Celsius, well, let's say that's somewhat up there. That looks good. The next thing that I need to do is figure out how many steps do I have? How many formulas do I need to use? What's going on here? So the first thing that I need to do is get from this 25 degrees Celsius up to the point of phase change. So from there to there, this point right here, this is going to be step 1. My next step is to actually go through phase change. So that is this section right here. That's going to be step 2. The last thing that I need to do is, after I get through phase change, is get up to 115 degrees Celsius. So that's going to be step 3. So I have my phase diagram. I know where I started, I know where I want to get to, and I've mapped out the number of steps that I need to do. The next thing I need to do is just figure out what formulas I'm going to use. So the formula that I need for step 1 is going to be Q equals MC delta T. So let's say step 1, and that's going to be Q equals MC delta T. And I know it's going to be that because I'm experiencing a change in temperature because I'm on a diagonal. So Q is equal to the mass, and the mass is 45 degrees Celsius. I know that the specific heat of water as a liquid is going to be 4.18 joules per gram degrees Celsius. And my change in temperature here is going to be from 25 degrees Celsius to 100 degrees Celsius because I can only go as far as the point where I hit the next phase change. So this delta T right here, my temperature final is going to be 100 degrees minus where I'm starting, which is 25 degrees Celsius. So 100 minus 25, that's going to be a delta T of 75. So if I multiply those three numbers together, my Q will be 14,107.5 joules. At this point, I ultimately know that I need to convert this joules into kilojoules, so I'm going to do that right now. So if I convert this into kilojoules, that's going to be 14.1075 kilojoules. So now I've done step 1. The next thing I need to do is go on to step 2. For step 2, that's a phase change. And this particular phase change involves the heat of vaporization. So I'm going to use the formula Q equals mHV. Now I have to be really careful here because if you look at the information that they gave you, the heat of vaporization that they gave us is in kilojoules per mole. So because my heat of vaporization constant is in moles, I need to take this 45 grams and convert it into moles before I can plug it into my formula. So 45 grams of water, multiplication sign in a line, the gram formula mass of water is 18 grams per 1 mole. If I work that out, it's approximately 2.5 moles of water. Now that I have that, I can plug it into my formula. So the number of moles is 2.5 moles times the heat of vaporization of water, which is given to me as 40.7 kilojoules per mole. And then if I work that out, I get that as 101.75 kilojoules. So now I've gone through step 1, I've gone through step 2, I'm totally through phase change. My substance is now all in the gas phase. I can go and do this last little part right here, which is labeled step 3. So step 3 again is on a diagonal, which means I'm going to use Q equals MC delta T. The mass still remains as at 45 grams. The specific heat of steam is different than the specific heat of water. So that is 1.84 joules per gram degrees Celsius. And my change in temperature for this one is going to be, my temperature final is going to be 115. My temperature initial is at 100 because that's where I ended up as I went through this phase change. So the difference here is going to be 15. So if I work this out, my final answer is 1,242 joules, which converted over to kilojoules, that is 1.242 kilojoules. My last step is to go through and add up all the energy values for each step. So for step 1, I ended up with 14.1075 kilojoules. For step 2, I ended up with 101.75 kilojoules. And for step 3, I ended up with 1.242 kilojoules. So my final step here, step 4, is to add all those up. So 14.1075 plus 101.75 plus 1.242, and if I add all those up together, my answer is going to be 117.1 kilojoules as my final answer. So this is an example of how you would calculate the enthalpy change in a phase diagram. So what did you learn in this tutorial? We went over a phase change overview. We did a little review of heating curves. We talked about calculating enthalpy changes in phase diagrams. We did a review of the formulas that were going to be involved. And finally, we did an enthalpy change practice at the end. Need more help? Feel free to contact me. Have a great day.